are down, power lines are down.
Message of 290 characters follows.
Hey guys, welcome into another episode of Grid Down Comms Up. I want to talk to you guys today about micro solar for off-grid communications. Sorry, it's been a while since I have put anything out. Been a little bit busy in my world dealing with replacing some underground cabling, getting a tree out of another tree, and lowering it to the ground. If you guys are interested in seeing some of those other projects, things I do that aren't necessarily radio related, feel free to post a comment, let me know, and I'll post some of that stuff. But I try to kind of keep this related to electronics and radio and survival and prepping stuff, but I can also throw some homesteading and other that kind of stuff in as well if you guys want to see that. So let's talk about micro solar, or solar for a specific purpose, not a whole house solar, not a multi-use solar system, but solar that's specifically for one task on a small scale, and in this case particularly to run our communications gear. Okay, my station, my ham radio station, my radio gear and non-ham radio gear and all that stuff runs off-grid 24/7, 365. Okay, I've not been connected to the grid in quite some time. In fact, a lot of these videos and podcasts that you hear me record, if I recorded them while sitting at my station, they were recorded on a laptop running off-grid. My laptop right now is running off my solar system. So let's get into this. We're going to talk about some of the things you may need to know, answer some of the questions and some of the different stuff about solar. We're going to talk about things you need to know to design your system to run 24/7 on small scale, and a little bit of how to do it cheaply. Okay. So first up, what applications would we want to run? Well, powering your home station we talked about. We also need to talk about powering your field station for emergency work. So if you need to go set up at a church, firehouse, whatever, a Harley-Davidson dealership, as we saw in Swannanoa a few years ago, and there's no electricity there, and you've got to provide power, well, that's another possible application in the field. And then we're going to talk about powering a portable station as well, for those of us that may want to carry it in a backpack and be able to walk around with it. And there's some good options there as well if you design everything to conserve energy. So why do we pick solar? Well, it's independence from the grid. That's why we use radio. We don't want someone else to be responsible for the things that we need that are critical, because they mismanage it, they don't do it correctly, and it's not really their concern when it fails. It impacts you much more than it does them in many cases. It is excellent for low power, long duration loads. So my ham radio station does not draw a ton of power. It draws about 3 amps on receive, and it does that for most of the day unless I'm transmitting. Okay. So works great for that. Generators and other big power making equipment do better at times for well pumps and other things, unless you want to build a truly massive solar system. They are sustainable for long periods of time. Okay, if you build a system at a good quality gear, get everything set up, you could potentially be looking at 10, 20, 30 years of lifespan for most of your components with minimal work from your side. So this is almost a set and forget. There is a little maintenance, but there's fairly low maintenance. So if the grid went down tomorrow, you would have many, many years before you needed to replace equipment potentially. It's quiet. There's no generators. There's no wind turbines. There's no anything like that that's making noise that can oftentimes, especially during the grid down, when it is very, very quiet outside. We don't realize how quiet it gets until there's no vehicles on the road and there's no air conditioners running, and you can hear stuff a very, very long way away. And communications is one of the few things that we really need electricity to do effectively. Yeah, sure, we can use bells and signal fires and horns and things like that to communicate over a certain distance. We're not going to communicate over extremely long distances with that, but over some distance without electricity. But we can heat our home, we can cook our food, we can heat water, we can do a lot of things using firewood and gas or propane or whatnot. But communicating is, especially with any sort of even semi-modern communications, is something that's going to require at least a little bit of electricity. So it's one of the things we really got to focus on. So what are the parts of an off-grid system? So if you're totally new to this and you don't know anything about solar systems or that kind of thing, these are the 4 basic parts. You have your solar panels that collect your energy from the sun. You have a charge controller that matches that energy to your batteries. You have batteries, which is your storage, and you may have an inverter to convert that DC power into AC to run, the equipment we are typically used to running off of AC. Now, I will tell you, in my micro solar systems, I do not typically have an inverter operating. All of my gear runs directly off of 12 volts in my ham shack. Everything from the desk lamp all the way to the radios and the laptops and the computer monitors, they all use only 12 volts or a 12 volt to USB-C adapter that gets them what they need from USB-C. And I don't use an inverter. The only time I really need to use an inverter in my shack is if I want to run my laser printer off-grid and print some stuff. So there are probably some other cases where some folks may need an inverter, but inverters are kind of optional in my particular system, and that saves me a lot of additional energy and design because 120 volt stuff sometimes isn't as efficient, and we have inverter losses that I really don't have to calculate because I don't have an inverter running all day. Okay, let's talk about solar panels. So the polycrystalline panels have been around for a long time. They're actually what I'm using. I got mine used for about $100 a panel. And I'll drop a picture of my solar setup in here. It's very primitive. It's very simple. It's some solar panels on a wooden rack sitting outside, and that's what runs my station all the time. I do intend to improve that, but it works for now. They are less efficient. They're typically 13 to 16% efficient for their surface area. They are cheaper. Like I said, I got mine used for a very, very good price. Shorter lifespan, and you can actually find them used now. I got mine a while back. You can find them used now for around $50 a panel. Shorter lifespan of about 25 years. So, and after 25 years, they still work. They just don't output quite as much power. So be aware, polycrystalline's really kind of an old tech, largely been replaced by newer, better stuff. But if you find them for a really good price and you're not trying to put them on a mobile vehicle, you're not trying to put them somewhere you're space limited, they're an option, especially for budget things. Monocrystalline. So monocrystalline is kind of the standard now. Now even more so with N-type monocrystalline that are even more efficient. Because currently, regular monocrystallines, we were seeing 15 to 20% efficiency. We're seeing up to 25% efficiency with the new N-type monocrystallines. So that's something that is worth looking at. If you're buying new to get the most efficient new panels, because they're price-wise they're not bad. Monocrystallines do tend to last a bit longer. They are a bit more expensive than polycrystalline, but frankly now they've gotten down cheap enough that they're really not worth looking at anything else unless you're looking at used and you're getting a really good price on it. And then let's talk about thin film. So thin film are not super efficient just by nature. They tend to be pretty big. They are lightweight. This is their win. For your portable operations, you're going to put it in your backpack. You're going to carry it around with you. Thin film is where it is at, particularly like solar film and power film stuff. If you're power film and you're listening to my video, I would love to be sponsored. You want to send me something? That would be awesome. I would love to have some power film solar panels. They're crazy expensive and really outside of my budget. But if they're in your budget and that's what you want to do, they're awesome. Go that way. They are very rugged. They can be they're less impacted by shade. So a lot of panels, if you get some shade on one part of the panel, you'll lose half or more of your output. The way that they design a lot of the thin film ones, if one of those little squares, you can see a thin film panel down here on the right. If one of those little panels gets shaded, it typically just drops that one offline, and the rest of them keep producing at a pretty good energy rate. But again, the downside is they are expensive. Charge controllers. All right, so we got to have a way to take that solar energy and we got to put it into our batteries. So the old school type of charge controller is pulse width modulation, PWM controllers. I actually have one of these little Renogy Wanderers that's up here in the top corner. I think I paid like $12 for it when I got it. Very inexpensive. They're probably $25 now with inflation and all the stuff that's gone on in the last 5 years. So they're a little bit more expensive, but they're cheap. They're not the most efficient when it comes to conversion. They don't produce as much power, particularly the morning and afternoon when the sun is a little bit lower on the horizon. They do require the panel voltage to be similar to the battery voltage, so it's going to limit your panel options when using these. And they may generate less radio frequency noise than some MPPTs because of just the way they work. But that's not 100% true. You can still get some radio noise. You just kind of have to design around some of those things, make sure you put proper suppression and that kind of thing. It really depends on what the modulation frequency of the PWM is. So if you know what that means, don't worry about it. Just realize that, yeah, they can still generate some noise, and it may require a little bit of filtering with some proper ferrites and that kind of thing. So MPPT, maximum power point tracking. This is probably the most common now. They are a little bit more expensive, but again, prices have come down a ton on a lot of this stuff. And MPPT is not quite as new of technology as it was when I put this presentation together about 5 years ago. So it's one of those things that they produce better performance earlier and late in the day. They're able to drag that last little bit of power or that first little bit of power out of solar panels into your batteries. And they work better on days with cloud cover when your panel voltage may be lower. In fact, my particular station set up here, I will still get 2 to 3 amps into my batteries even when it's raining outside. Maybe only 1.5 amps, but usually between 1 and 3 amps even when it's raining outside. So that's one huge benefit of those. They may allow for the use of higher voltage panels for more efficient systems. We'll get into the higher voltage part in a minute, but if your panels are a long way away from your batteries and your charge controllers, using higher voltage in the cabling reduces losses and makes the system overall a lot more efficient. And it opens up the option to use some of the more common grid tie panels and those sorts of things. In the picture over here on the right, you'll see this Genasun charge controller. If you are looking for a totally dead radio silent charge controller, the Genasuns are the ticket. Unfortunately, they're only a 10 amp controller, which limits their usefulness. I use them in portable operations a lot. I actually own 3 or 4 of the things, and they're, like I said, they're expensive, but they are worth it, especially for those sorts of applications. Probably the best controller out there. They also have an extremely low idle use, so if you have it in a battery bank or battery box that you're not using every day, it's not going to kill your batteries in a few days, weeks, or even months, the way some controllers would. All right, let's talk batteries. We're going to go over lead real fast because when I created this presentation, lead was still a thing. Now lithium has come down to such a cheap level that almost nobody's using lead. I wouldn't use lead. So there's flooded batteries, AGM, which is like a absorbed gas mat. It's like a fiberglass mat the electrolytes in, and gel batteries. Gel batteries, again, it's another one of those things, they don't spill. They're old tech. Charging them is... it makes them easy to damage. You can overcharge them and harm them. You can discharge them too much and harm them. You can charge them too fast and harm them. There's charging requirements. Lithium's got some difficult charging requirements, but lead has a lot of issues as well on that front. They don't last as long as lithium in most cases. You can get really nice lead batteries, and people used to do this and get them to last for 20 or 30 years. But you end up with huge extra amounts of capacity because of their high internal resistance, their fact that they don't hold their nameplate charge if you discharge them quickly. There's all kinds of things that change that make oftentimes really big lead arrays, and frankly, they're not cheaper than lithium now. So most folks have moved beyond lead, and we're just going to leave it at that. Let's talk about LiPo4s, or other lithium technologies, lithium ion, etc. They were more expensive up front. They're still in some situations a little more expensive, in others not so much. They are very low maintenance. You kind of hook them up and forget about them. With just check your terminals once in a while, make sure they're tight, and don't do things with them you're not supposed to do, like charge them below freezing. Though most have protection for that now. You can even get them to have heaters, so they'll warm themselves up before they start charging. The cycle, the charge-discharge cycle, is more efficient with lithium. You have better voltage stability. Our radio gear really likes lithium because for most of its charge-discharge cycle, it stays above 13 volts, which keeps our radios much happier than the leads that get down around 12. They're lightweight. They weigh a teeny fraction of what lead batteries weigh. And the max charge discharge rates are often significantly higher without taking any penalties than lead batteries are for their size. So personally, I'm running 2 Battleborns. I'll show you a picture here of the 2 Battleborns that are on my station. I know about the Battleborn drama and everything that's going on. For those of you guys that are kind of watching that stuff, time I bought my Battleborns, really the only options you had that were of any quality and trustworthy were Battleborn and Dakota. I flipped a coin, bought Battleborns. Kind of wish I'd went the other way. I may end up replacing my Battleborns at some point in the near future, and if I do, I'll probably add another 100 amp hours just for a little more cushion of the wintertime on my setup. But yeah, this is what I'm running. This is what runs my station off grid all the time. 200 amp hours of batteries and 500 watts of solar panels and a 40 amp charge controller. So, all that stuff now with current lithium battery prices, if you buy used panels, you can get everything that you need to operate off-grid 24/7 for most folks, sub $1,000. So less than a decent HF radio will cost you. You can take your station off-grid. And to give you an idea of what my station is like, I have an ICOM 7300 HF radio. I have a dual band VHF UHF. I have a commercial UHF radio running. I have 3 Raspberry Pis running and a low power Intel N150 laptop running. All that stuff runs all the time. I also charge my HTs off of the same solar system, and my flashlight and night vision and other application batteries off of the solar system as well. And that's all I need to do this. So it's not cost prohibitive to get your communications off grid. It does require some careful selection of equipment and that kind of thing. I went ultra low power with a lot of my gear when I purchased it because batteries were expensive back then, and they're cheaper now. So the calculus has changed a little on that. I also have in batteries here others listed: nickel cadmium, nickel metal hydride, some other stuff. They're not really common in this type of application. They're more of what you'd find in an older HT battery or something like that. We don't really run larger scale solar off that stuff normally. So how much power do I need anyway? Well, first you need to determine how much power your station is using. You can use the nameplate or the manual information for your gear. That is a way to do it. I have found that to sometimes be wildly inaccurate. So I would just encourage you to pick yourself up a decent clamp-on ammeter. I'll show a couple of clamp-on ammeters here that aren't too bad and vary in price from easily affordable to, unless you do this professionally, you probably don't need it. But I would just do that, determine what my actual station usage is. Next, you got to determine your duty cycle. And duty cycle is how long am I transmitting versus how long am I receiving, because that you have to calculate that. I've got a worksheet that kind of helps calculate that stuff. I'll try to post some way it in the comments if I can. And I'm going to do another video where we walk through a sample of how to calculate this stuff. If you're allergic to math, I apologize, but there's no way you're going to get through this without doing some math and not just be wildly guessing at what you need. So the common things you're going to run into needing to understand here are volts, amps, amp hours, watt hours, etc. What does all this crap mean? Well, volts is the voltage. It's the push on the electricity. It's how hard does it want to push. It's like water pressure. Amps is the volume. Amp hours is a unit of storage. So it's how many amps for a certain number of hours can a battery produce. So if you have a 100 amp hour battery, in theory, it could produce 100 amps for 1 hour, or 50 amps for 2 hours, or 25 amps for 4 hours. You get the thing. Watt hours, watts are volts times amps. So they give you a power unit that is not connected to voltage or current, and that can make the math easier, particularly on big solar systems where your voltages are changing a lot. In our micro solar for ham radio communications, whatnot stuff. You can use that if you want to. I usually just use amp hours because my voltage standard across the whole system is 12 volts, so it's not too bad. How far can we safely discharge your batteries? Well, this used to be relevant more so because lead batteries, if you discharge them more than about 20%, you reduce their lifespan. And if you discharge them more than about 50% of their capacity, you greatly reduce their lifespan. Lithium's a lot more forgiving than that. You can completely discharge lithium batteries without significantly harming them. And even if you discharge them to like 80% of their capacity, you will still get 4,000 or 5,000 cycles out of them before they get to 80% capacity. And even then, they're still serviceable. So very different now. So a lot less of a concern than it was with lead. That's one of the reasons I went with lithium. I was going to need 400 amp hours of lead, maybe even 600 amp hours of lead to get the same lifespan and capacity that I got out of 200 amp hours of lithium, just because I needed to have that extra cushion to not harm the lead batteries. So important things to understand there. We are not going to talk about Buchardt's Law because that is really only relevant to lead batteries, and like I said, nobody's really using that anymore. So we're going to collect that power. How many solar panels do I need? Well, we can use the watt hour thing to figure that out, or we can figure out how many amps an hour we need. Again, the worksheet that I've got kind of walks you through calculating some of this stuff, but we have to figure out how many watts we need to replace what we're taking out. And again, we can kind of convert that if we have 120 watt. We'll just do a 120 watt solar panel because this makes the math easy. For a 120 watt solar panel, well, at 12 volts, that's 10 amps. So that means that panel could, in theory, put 10 amps of power back into our batteries. What is solar insulation? So this is something that you have to figure out based off where you're located. It's how much power do we get at any given time of the year. So obviously the day's length changes, the height of the sun and the sky changes throughout the year for most of us. And we have to look at that to determine how much solar power, how much energy from the sun is available at any given time of the year. and we have to design our system around the worst case of that for stuff that is mission critical, like communications. We want to make sure that in December, when the sun doesn't come out in my area for 3 days, and we only get about 4 good hours of solar anyway, that we have sufficient solar panel capacity to recharge our system during that time. Now, a lot of people that are completely off grid will make the decision that, particularly if they're in more northern latitudes, that they will just run a generator for a couple months out of the year, maybe once a week, top off their batteries if they have a particularly cloudy week, because it's cheaper than all the additional solar. So that's something that you've got to make a judgment call on with your ham station. Me, I built mine so that it will run all my critical gear for a few days, and I just kind of turn off some of maybe the less needed Raspberry Pis and other gear during that couple of weeks to reduce my power consumption, and don't charge batteries and that kind of thing if I can avoid it until the sun comes out. So design around the worst case scenario like we were talking about. Now you got to pick that charge controller. That's determined off of how much power you need to put back into your batteries, and what voltage your panels run at, but mostly the amount of power you want to put back into your batteries. So what's the maximum current you need to put in? And you need to pick a charge controller that can do that. So that's pretty straightforward. Charge controllers come in ranges from 5, 10, 20, 30, 40, 50, 80, 100, 200 amp charge controllers, depending on what you need. And then I squared R equals watts losses. We need to talk about this a little bit. I know it's math. A lot of people don't want to talk about math, but it's important that we understand how this affects their system, because a lot of people have built systems in the past and then they can't figure out why it's not performing the way they thought that it would. And oftentimes it's because they have very high internal losses and they're wasting a lot of the energy that they are producing. So I'm going to give you an example here. So if we have 50 feet of 2-conductor wire, what you would run to your solar panels, and we use 14 gauge wire. I know that's a little small for what most people are running to their solar panels, but we're going to use it in this example. That means we have 100 total feet of wire, because we have 2 conductors 50 feet long, and 14 gauge has 2.5 ohms of resistance per 1,000 feet. So at 100 feet, we would have 0.25 ohms. Now, let's do some sample calculations here and look at what this does. So if we put 5 amps through that 14 gauge wire, and yes, I know the National Electrical Code says we can put up to 15 through it, but they're also not doing the loss calculations for voltage, because you have to do that separately, and we're not going to get into that. But anyway, at 5 amps, we get 5 squared times 0.25 gives us 6.25 watts of loss. So we have at 5 amps of current flowing, and it doesn't matter what the voltage is. That could be 100 volts or it could be 5 volts. We still lose the same 6.25 watts. With 10 amps, we lose 25 watts. At 15 amps, we lose 56 watts. Well, this is important because the lower our system voltage is, the greater the percentage of the power we're producing that is. So if we have a 1,000 watt array, losing 56 watts, not a huge deal. But if we have a 200 watt array configured at a very high current level, losing 56 watts is kind of a big deal. So let's look at these losses at some different system voltage. So if we take approximately a 19 volt system, which is what we would typically find in a 100 watt portable solar panel, and typical of what we would use with one of those PWM controllers that need power at a similar voltage to the batteries. So 19 volts, and with lithium, our max voltage we're going to put into the battery charging is about 14.5 volts. So it gives us about 4.5 volts-ish over our system battery voltage for the controller to function. So if we look at that, a 100-watt panel will deliver about 93.75 watts at the end of that 50-foot run of 14-gauge wire. However, so we're about 93% efficient. Now, we all know a 100-watt panel is never going to produce 100 watts, but just for conversation's sake here and to keep the math easy, we're just going to go with that. And then 300 watts at the same voltage with the same wire, if we crunch the numbers, will yield about 80% efficiency, only delivering around 240 watts because we have tripled our current flowing through the wire, and it doesn't just simply triple the loss. Now let's take a look at the same with a 300-watt system at a higher voltage. So this time we're going to look at a system with 57 volts, very similar to the system that I am actually running on my ham station, and the same 50 feet of number 14 wire. So if we crunch the numbers, we end up losing only about 6.25 watts during the cable run, as making it approximately 98% efficient, as opposed to the previous example at 19 volts, which was much less efficient, costing us approximately 55 more watts in losses. So 55 more watts, that would mean we would only be delivering about 245 watts out of the 300, or we would be losing about 1/6 of our power to heat and loss in the wiring. That is a significant difference from 19 to 57 volts on the same size wiring. So this is why this is important to consider. So if you were to double that length of wire and make it a 100-foot long circuit, you would double those numbers and be losing more than 1/3 of your power at 19 volts, as opposed to with the higher voltage, you would only be losing about 12.5 watts. So very important to understand, very important to consider when we're building your solar systems, because this is how folks end up, why is my solar system not performing well? Well, it's because they're potentially losing 1/3 of their power in voltage drop and current losses and the I²R losses. So just very important thing to keep in mind. Let's talk about inverters for just a minute, guys. Said I don't use an inverter. Some of y'all may want one. I have an inverter. I can connect it up to my system if I need to run my printer or something that's only 120 volts. But otherwise, I don't really use one. So, because they can generate RF noise and cause a lot of other issues, and I just prefer to design around them. But there's pure sine wave versus modified sine wave. Again, I did this presentation for Heritage Life Skills about 6 years ago. So there's no point in buying a modified sine wave inverter at this point. There's plenty of inexpensive pure sine wave inverters out there. So we're not even going to talk about modified sine wave inverters. Just buy a pure sine wave inverter and just be done with it. I have a Victron 1200 watt inverter over here that was a couple $100, and you can get sub $100 if you just need a few hundred watts to run a couple little things. Sometimes we can't avoid inverters. Like I said, you run in my laser printer, it's 120 volts. It is what it is. Sometimes we want to run a refrigerator or something else. We don't want a spring for a 12-volt fridge because 120-volt ones are cheaper. We need an inverter. Maybe that's your situation. You're not building micro solar to run your communications gear. Maybe you're building micro solar to keep your refrigerator with your insulin in it cool. And, then you're going to need an inverter. So, they're out there. There are a lot of good ones that aren't crazy expensive. I like Samalex. I use Go Powers at work. I like my Victron, and I've even got like a couple cheap what is this one? I've got like a Gandil or however you pronounce it that I picked up for like $40 on Amazon to stick in my truck and run my DeWalt battery chargers off of. It's, you know, there's a lot of options out there. You just got to make sure you size them right if you're trying to start a refrigerant compressor or something like that in a refrigerator. Suppressing noise, for those of us doing radio, is a thing with inverters. If the inverter's well designed, it's shielded, it's going to help a lot. Also, you may need to put some ferrites to choke off any unwanted noise on the power leads for DC and for AC. So just one of those things. And I hope you guys found this helpful. I hope you guys learned a little bit. You know, again, I do some pictures of my station in. Going off grid is not a huge deal and not crazy expensive anymore for your communications. And one of those things that really is critical if you want to stay in the know when the grid goes down. Even if you're just putting together a 100-watt solar panel and a little battery and some stuff to charge some AA batteries so you can keep your shortwave receiver running. Whatever it is, you can build a small system that will make a huge difference if the power is out in knowing what is going on, keeping you aware of what is going on around you, or just keeping some HTs charged so that you can keep in contact with the neighbors down the road. 7-3 guys, hope that you found this useful. I will put a link in here to the other video that I did on calculating a little more in-depth the math side of things. Remember to like, subscribe, and share. Helps the channel grow, helps me get to more people with what is hopefully some real-world useful information in the survival preparedness space and not just the adrenaline and whatever dump of things to be afraid of. Let's do practical solutions on how we can improve our position and preserve the quality of life and lives of those that we love. See you guys on the next video.